Good evening, everyone. Welcome to the 12th week of NPTL Analog Communication Problem Solving. So, today is the final problem solving session for this course, and today we will cover the topics that has been taught in week 12 of the NPTL Analog Communication uh, class. So, with that, we'll get started. Now, the 12th week of NPTEL analog communication is dedicated to sampling theory. So, today's topic is sampling theory. So, today's topic is sampling theory. So, which of the following accurately describes the effect of sampling in signal processing? So, what is the effect of sampling in signal processing? That is the first question. Option A, it discretizes the time dimension. B, it converts analog to digital. C, it converts continuous time to quantized signal. And C, it performs amplitude quantization. Now, sampling affects on the time domain axis, not on the amplitude. So, if there is a signal like this, the time domain samples work like this. So, time domain samples will come like this, and you take this. So, this is a time domain sampling of our analog signal. Now you convert this you converted basically a continuous time signal to a discrete time signal, but the amplitudes are not getting discretized, so it is not converting an analog to digital signal. Neither is it converting to a quantized signal. Neither does it perform amplitude quantization. So the correct answer is option A. It discretizes the time domain signal. A television signal. Second question is that a television signal is sampled at a rate 30% above the Nyquist rate. The signal has a bandwidth of 8 MHz. The sample are quantized into 2048 levels. The minimum bandwidth required to transmit the signal. Hmm. Uh, a television signal. A television signal is sampled at a rate 30% above the Nyquist rate. So the signal has a bandwidth of 8 MHz. The samples are quantized into 2048 levels. The minimum bandwidth required to transmit that signal will be you have the sample. Okay, so a television signal is sampled at 30% above the Nyquist rate. So if the Nyquist rate is 2 into B, the Nyquist rate is 2 into B. So a sampling rate above 30% above Nyquist rate means 1.3 times the Nyquist rate. That is 1.3 into 2B. So 2.6 times the bandwidth. So 2.6 times the bandwidth. Now the bandwidth is given to be 8 megahertz. So it is 2.6 into 8 megahertz, which is 2.6 into 8 megahertz, which comes to which comes to be 20.8. 20.8. 20.8 megahertz. So the sampling rate is 20.8 megahertz. Now it is the samples are quantized into 2048 levels. So the sampling rate is 20.8 megahertz, mega samples per second. Now the samples are quantized into 2048 levels, which means 2 to the power 11 levels. So if we want to represent it in bits, it will be 11 bits representation. So the bandwidth required for transmission uh, sorry for the network disruption. So yes, so the bandwidth required, sorry for the network disruption, bandwidth required will be 11 bits into 20.8 million samples, mega samples per second. So it is 20.8 mega samples per second, and this is 11 bits per sample. So sample gets cancelled. So 20.8 into 11. 20.8 into 11 is 228.8. 228.8 mbps, megabits per second. This is the bandwidth that is required. So it is 228.8 megabits per second. So option A. Okay. Next, if the number of bits in a PCM system increases from n to n plus 1, the signal to quantization noise ratio will decrease by a factor of. So here we get introduced with the concept of PCM or pulse code modulation. So now we will go through the basics of pulse code modulation. So So the task of pulse code modulation is to convert the codes that we have into quantum levels, into levels that are discrete levels. So we convert the analog signal into discrete levels in pulse code modulation. So how we do that is a three-stage process. So PCM is actually a PCM is actually a three-stage process. The first stage is sampling. The second stage is quantization, and third is modulation. So, or this modulation is also called encoding. So, this converts analog signal, CT analog signal. So, what we have is a continuous time analog signal, CT analog signal. Now, our first aim is to convert this into a CT, or rather not CT, DT. So what does sampling do? As from question 1, we can say that sampling converts continuous time to discrete time. So we have a DT analog signal. Now once we have the DT analog signal, then quantization does DT digital signal. So now quantization converts analog signals to digital signals. So we have now a DT digital signal. And then we have a DT encoded signal. So here usually we use binary encoding. So we have a DT binary signal. So usually we do binary encoding. So we will have a DT binary signal. So this is a DT encoded binary signal. So these are the first three steps. So the first step, so in the first stage of PCM is first stage of PCM is to so the first stage of PCM is known as the sampling. So with sampling we have this continuous signal. We want to sample it. We will take samples of this curve at a fixed interval like this. So what we will have is this curve. So this is sampling. So here so this is the sampled signal. So this is the sampled signal. Now what we have here in the first stage, after the first stage of PVCM, is a discrete time signal. So here we have a discrete time signal like this. The envelope of this discrete time signal gives you the actual signal that was transmitted. Now that one was straightforward. The next stage of PCM is quantization. Rather, let's do it here. Second stage of PCM. Second stage of PCM is quantization. Sorry, quantization. So here, while we have discretized the time domain, but we have not changed anything in the amplitude domain. So আহ, এইখানে আচ্ছা 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 আহ, আচ্ছা 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 এটা হয়ে যাবে এক্ষুনি আচ্ছা আচ্ছা ঠিক আছে ঠিক আছে pause করে দিচ্ছি। আচ্ছা, দেখ কি এসছে হ্যাঁ না ঠিক আছে ঠিক আছে okay so for the next stage now we don't have any control over the levels of these points. So this point can be here, can be here, can be here, can be here, anyway. So the value, the y-axis still remains. Our task is to restrict the values of this data into small discrete chunks in both time and amplitude domain. So next we will do the same thing in amplitude domain. We will restrict the amplitudes. So it's, these two are pretty close together. So instead of giving two separate levels for these two, what we will do is we will give them the same level. So here also, whatever the value is there, here also we are assuming the same value is there. But from here to here, there is a substantial increase. From here to here, let's change the marker color. So from here to here, there is not much increase, but from here to here, there is a lot of increase. So we can change the level now. We can say it is in this level. Next, this and this again has the same level. So we will say both of them fall in this category. Next, this again falls down. So we can say it is in this level. And from here to here there is a sharp drop. So these two cannot be in the same level. So further another drop will be there. And these two are again nearly on the same level. So here we see that we had 1 2 3 4 5 6 7 7 levels. Here we had 7 levels because there were 7 samples. As many samples are there, that many levels will be there unless two samples values are equal. So here we had 7 levels. Now here we have 1 2 3 4 4 levels. So quantization compresses these levels. Now why do we need to compress into these levels? Because the less number of levels you have, the less you have to deal with the sensitivity of the receiver. The less sensitive receiver also can easily detect, and further there will be a robustness to noise, because here if there is a slight noise then it can corrupt the value of the sample, but here since we are considering these two to be same, so here a bit of noise won't change the level. As long as there is not a noise large enough to switch the level of the signal, we can say that the noise is it is robust to noise. So it gives less computation quantization advantages. One, it involves less computation, and another is it is less, or rather not less, more robust to noise. More robust to noise. Now if there are advantages, there will be disadvantages. So the disadvantage here is that you have to lose information because 7 levels had more information than 4 levels. So we are losing out information. And next is encoding. Here, instead of giving raw voltage values, we convert third stage of PCM is encoding. Encoding. Now here we convert raw voltage values into symbols. Either you can say symbols or you can say blocks of bits. So here we have 4 levels. So the natural choice will be, because we have like this, this, this. So since now this is our signal versus time, so the natural choice for 4 levels will be 2 bits. So we can have 00 to represent this level, 01. So here raw voltage into mapping. So encoding is basically mapping. It is not discretizing anymore, it is mapping. So 0001, this one will be 1011. So we have mapped the 4 levels, 4 quantization levels into 4 symbols. 4 symbols or blocks of bits. So we have converting 4 quantization level into 4 symbols or blocks of bits. Now we can transmit this. So here you see, for 2 durations there was 00. For 2 durations there was 01. If we recall that 2 samples map to 00, 2 samples map to 01, 2 samples map, 1 sample map to 10, and 2 samples map to 11. So the final PCM coded bit stream, PCM coded bit stream will be 0 0 0 0 0 1 1 0 0 1. Sorry, 01 is also 2 times. So it is 0 0 0 0 0 1 0 1 0 1 1 1. So this is the final bit stream that represents this. So PCM converted. So what did PCM achieve? PCM converted this analog signal, this PCM converts this analog signal to 0 0 0 0 0 1 0 1 1 0 4 ones. So it converts this analog signal into this digital bit stream. So this is the overall effect of PC. With that, we will go back to the problem. So here, before we can address the problem, we see that we need to do some math regarding the PC. So we have to derive some values for the quantization error and other factors. हाँ बोलो क्या हुआ फोन ठीक ठीक okay uh, so here uh, sorry where was I yeah so you can see PCM consists of three steps, which is sampling, as we have discussed, and encoding. So during quantization, there is a normal quantization is there, which is step by step quantization. Another way of quantization is a continuous quantization, which uses a mu law or a law compressor. So the hmm, the use of non-uniform quantization, the quantizer is equivalent to passing the baseband signal through a compressor and then applying applying uh, the compressed signal to a uniform quantizer. So what we have used previously is a uniform quantizer, and now we will be in this. You can see it is a non-uniform quantizer, but non-uniform quantizers we will not be going into details. Instead, we will consider the quantization noise. So in PCM system, there are two kinds of noise. One is the channel noise, which is introduced anywhere between the transmitter output and receiver input. So this channel noise part, this is independent of the transmitter which is it is independent of the PCM system. So channel noise will always be there. So whether you use PCM or you use some other communication protocol. And another part of this is the quantization noise, which is unique to PCM, because you are say quantizing 17.93 as 15 volts. So everything between 15 to 20 volts you are quantizing say as 17.93. Sorry, anything between 15 to 20 you are quantizing as 15 volts. So anything between 15 to 20 volts you are quantizing as 15 volt. So this is the quantization you are doing. Now in this quantization, if your input voltage comes out to be 17.5 say, then your quantization noise will be equivalent to So you are losing out that information, and that is represented in the format of quantization noise. Naturally, these two noise sources appear simultaneously once the PCM system is in operation. But the traditional practice is to consider them separately so that for the ease of analysis, we consider them separately. So, the main effect of the channel noise, which is to introduce bit error, is not considered here. Here, we only consider the quantization noise. Because so here we have quantization noise only we will consider. Next, So, so next we will go into the quantization noise of an analog signal. So there are two types of uniform quantization. One is uniform quantization and one is non-uniform quantization. For uniform quantization, the step size, that is the size between these two steps, is the distance between these two steps rather. The so there are two types of quantization. One is uniform quantization another is non-uniform quantization. So in uniform quantization, the step size is constant with respect to input voltage. And here step size varies according to mu law or A law. So there are two kinds of curves by which the step size varies according to mu law or A law. The input voltage varies according to with step size according to these two laws, mu law and A law. Mu law or A law. Step law varies, step size varies according to mu law and A law with respect to input voltage. So what is mu law and what is A law? So here you can see the expression for mu law and A law. Mu law is given as the step size as log 1 plus mu by m into divided by 1 plus mu, log 1 plus mu. So m is the input voltage, so log 1 plus mu by m by log 1 plus mu, where mu is a positive number, is known as mu law. So for mu equal to 0, it is constant, so there is no compression. Whatever the input is there, that is the output. Whereas for mu equal to bigger and bigger values, this output compresses with respect to input. So this is the mu law. And another is there, which is the A law. A law gives A mod m by 1 plus log a if the input is less than 1 by a, and if it is greater than 1 by a, then your the modulation is given as 1 plus log a m by 1 plus log a. So here what we see is that this uh, this has a linear variation as long as the input is within a particular range of 1 by a. Beyond that, it is similar to mu law. So as long as this a is small, as long as this a is smaller than 1 by mod m, as long as the a is smaller than 1 by mod m, you will have a linear kind of relation. But the moment it is bigger than 1 by mod m, a is bigger than 1 by mod m, you have mu law. So at small a values, you can have a kind of linear compression rather than straightforward mu law compression. So this is non-uniform quantization. Now, once we have here, but here in uniform quantization, the main parameter of importance is step size. According to where the step falls at origin, there are two kinds of quantization. One is called the mid-rise quantizer. One is called the mid-rise quantizer, and another is called the mid-step quantizer. So, in mid-rise quantizer, at the origin, the input versus output curve, we plot voltage input versus voltage output. So, at origin, let's plot it using red. At origin, it is rising and then it is going to this value, then this value, then this value, then this value, and here also this value, then this value, then this value. So this is a mid-rise quantizer, whereas in a mid-step quantizer, the origin, or when we are in equal to 0, the origin will be inside one quantized level. So the 0 level is also properly quantized. So here the 0 level is also properly quantized. So usually this mid-step quantizer is preferred because at 0 voltage it gives 0. So V out equal to 0 at V in equal to 0. Whereas the exact value at V out equal to 0 for this one can be anything between this part to this part, that is delta, plus delta by 2 to minus delta by 2. So if Vn equal to 0, V out will be within plus delta by 2 to minus delta by 2. So this is not preferred. Here at V out equal to 0, at Vn equal to 0. So mid-step quantizer is better preferred. Now this size known as delta, step size. This delta is useful in explaining the quantization noise. So now we will be focusing on the derivation of SNRQ, or rather SQNR, which is signal to quantization noise ratio. Now the quantization noise is basically whatever your x particular value is deviating from the actual, from the quantum level. So the quantum is say at delta by 2 for a mid-rise quantizer. The quantum is at delta by 2. So the quantization noise is x minus delta by 2. So here, whatever is your value is, the quantization error is basically the value minus the quantization level. So this part is called the quantization noise. So here, Here you can see that the quantum levels are separated by, so here the delta v by 2 to minus delta v by 2. So whatever the noise error is, so it will lie within, so here your value is, say your value is here, so whatever your value is, your value will lie within this point place. So if your value is here, so your quantization error will be with respect to this portion. So either from here to here, or from here to here, either from the lower step or from the upper step. So it will always be within minus delta by 2 to plus delta by 2. So quantization noise lies between minus delta by 2 to delta by 2. Now, we don't know anything about the distribution. So we can assume that between minus delta by 2, since there is no particular bias, we can assume that between minus delta by 2 and delta by 2, it is uniformly distributed. So quantization noise Q, so it is Q distributed as uniform minus delta by 2 to delta by 2. So the quantization noise power is given as E Q square minus EQ whole square. So here, or rather it is just EQ square. So EQ square is variance of Q. This is the quantization noise power. Let's recap. So if the quantization noise Q is distributed as uniform, so quantization noise power is EQ square. So it is Q square 1 by, and what is the uniform distribution PDF? It is 1 by B minus A. So it is like this dq. And what will the quantization noise vary from? Minus delta by 2 to delta by 2. So it is q cube by 3 delta between delta by 2 and minus delta by 2. So it will be delta square by rather delta cube by 8 minus of minus, so plus delta cube by 8 by 3d. So it will be delta square by 12. Now the variance, will be delta square by 12 minus the average is 0, so it is delta square by 12. Now, so variance is also delta square by 12 anyways, so that's not the point. So here the noise quantization noise power is delta square by 12. Now we come to the signal power. Now here the peak value is represented as MP. So let's assume this is MP. So this is MP. So this will be minus MP. So the signal is restricted between minus MP to MP. So let signal lie between minus MP to MP. Now you want to make L levels, and there are L levels of quantization. L levels of quantization. So what will be the step size? Step size is the total range, which is 2 MP divided by L. So the quantization noise is MP's 4 MP square by 12 L square, or 3 MP square by L. This is the quantization noise. So the SQNR rather will be the signal power. And what will be the signal power? The signal power will be something like uh, M square T RMS. So let's just keep the signal power, since the signal power is not in the hand of the quantizer. So we can just put the signal power as some S, capital S. So it is capital S into capital L by 3 MP square. This is the expression for SQNR. Now we come to our question. If the number of bits, so number of bits increasing means number of levels increasing. If there are n bits means how many levels? N bits means 2 to the power n levels. Whereas n plus 1 bits means 2 to the power n plus 1 levels. Now, the SQNR is dependent on the signal power S, the number of levels L, and 3 MP. Now the maximum range of the signal remains same. This is constant. And the signal power is also constant. Only how many levels we are dividing the signal into is changing. So SQNR is directly proportional to L. So if L dash is, so if L1 is 2 to the power n and L2 is 2 to the power n plus 1, then SQNR2 by SQNR1 is equal to L2 by N1. So L2 by L1 is 2 to the power n plus 1 by 2 to the power n. So it is 2. So SQNR2 is equal to 2 times SQNR1. So the SQNR will also get doubled. Sorry, this is L square, 3 MP square by L square. So this is square. I think I made a mistake here. This will be square. So 3 MP square by L square, not M. SL square by MP square. I'm sorry. So this is proportional as L square. So here it will be L2 square by L1 square. So 2 to the power 2n, 2 to the power 2n plus 2 by 2 to the power 2n. So it is 2 square. 2 square, that is 4. So the correct answer is 4. Next, a PCM system uses a uniform quantizer with a followed by a 10-bit encoder. So the bit rate of the system is 5 into 10 to the power 10 bits per second. So what is the maximum message bandwidth? So there is a 10-bit encoder. So each sample has 10 bits. Each sample has, so here we see that PCM system will use the uniform quantizer followed by a 10-bit encoder. So there is a quantizer. It will create, say, 2 to the power 10 levels because there is a 10-bit encoder. So it has to create at most 2 to the power 10 levels. So it can create less than that, but it cannot create more than that. And then there will be a 10-bit encoder. So each sample has 10 bits, and the output data rate is 5 into 10 to the power 7. So the sampling rate Fs is given as 5 into 10 to the power 7 bits per second and 10 bits per sample. So 5 into 10 to the power 7 by 10 samples per second, which is 5 mega samples per second. 5 into 10 to the power 6 samples per second. So there are 5 mega samples per second. And the bandwidth. So this has to be at least the Nyquist rate. So it has to be at least twice the bandwidth by Nyquist theorem. This is the Nyquist theorem. So at least Fs equal to 2b implies D is 2.5 megahertz. 5 mega samples per second divided by 2, so 2.5 megahertz. Next, consider a signal that ranges from minus m to m. So here the peak is mt is m. It is quantized by a quantizer with L levels. So we have seen the quantization noise, we have derived it just now. So the quantization noise is 3mp square by L square. 3mp square by L square. So it is rather, sorry, mp square by 3L square, not 3mp square by L square, mp square by 3L square. So mp square means n square and 3L square means 3L square. So here the correct answer is n square by 3L square. So correct answer is option C. Next, the Nyquist sampling rate of sync 800 pi t plus sync 600 pi t is, so here we have two signals with separate bandwidths. So the first one has a bandwidth of 800 pi t. So it goes from 400 to minus 400. And another is per turn goes to 300 to minus 300. So the 300 to minus 300 signal will be subsumed under the 400 to minus 400 signal. So we need to emphasize on this. So twice this will give you the Nyquist sampling rate. So 400 twice is 800. So 800 megahertz. Next, there is one signal sync 2 pi f1t, another signal sync square 2 pi f2t. So the Nyquist sampling rates are, for xt it is simply f1 2 times. So here the xt is given as this. f1 to minus f1. So the bandwidth is 2. So bandwidth is f1, so sampling rate is 2. Second is sync square. Now for sync square, the principal lobe for sync square will go up to 2f1, rather 2f2, sorry, 2f2 to minus 2. So the bandwidth will be 4f2. So 2f1 and 4f2. Now for the same xt and yt, the sampling rate of xt plus yt. So the sampling rate of xt is 2f1 and sampling rate of yt is 4f2. So which one will be greater? The other one will be subsumed. So Nyquist theorem states that we have to take the highest frequency. So the other frequencies which are not the highest can easily be not considered for the calculation. So whichever is higher among the two Nyquist rates will be the effective Nyquist rate. Among Nyquist rates of xt and yt will be the Nyquist rate of xt plus yt. So the Nyquist rate of xt is 2f1 and the Nyquist rate of yt is 4f2. So it will be the maximum of 2f1 and 4f2. So 8 correct answer is option D. Now the Nyquist rate for the signal sine square and sine into sine cube. So the cube will increase the bandwidth 3 times, whereas the square will increase the bandwidth 2 times. So this one will be 4000 pi t, means it is 2000 hertz, because 4000 pi by 2 pi. So whatever is in the argument you have to divide by 2 pi. So it is 2000. So 2000 is the maximum. So into 2. And here it is 1000 is the maximum. And you have to multiply by 3. Now these two bandwidths will get added because the signals are getting multiplied. So these two bandwidths will get added. So finally you will have 4000 plus 3000, which is 7000. So 7000 will be the final spread. So 7000 into 2. Now 7000 is the system bandwidth. If this is the bandwidth, then Nyquist rate will be twice of this bandwidth. So it is 2 into 7000, which is 14k. So it is 14k. Finally, 24 voice signals are sampled uniformly. So 24 voice signals will be sampled uniformly at 8 kHz and then sent using TDM, or time division multiplexing scale. 24 voice signals are sampled uniformly at 8 kHz and then sent using TTM scheme. The sampling processes use flat top samples with 1 microsecond duration. An extra pulse of duration 1 microsecond is added for the purpose of synchronization. So the sampling process uses flat top sample with 1 microsecond duration and an extra pulse duration of 1 microsecond is added. So each signal will have 1 microsecond, then it will have 1 microsecond extra. The spacing between two consecutive samples is. So the sampling interval. So first we have to find what is the sampling interval. The total number of signals that will be sent is extra pulse is sent 24 plus 1. So 25 signals need to be sent. So in total 25 signals need to be sent. And the total sampling duration. So total sampling duration is one sample duration. You have to send all the signals in this one sample duration. So the total sampling duration is 1 by 8 kilohertz because it is sampled at 8 kilohertz. So it is 1 by 8 kilohertz, that is 0.125 millisecond, or more conveniently 125 microsecond. So if 125 microsecond is the sampling duration and you have to send 25 signals. Now there is a extra, so 25 signals, each signal will have 1 microsecond duration. So to send 25 signals of 1 microsecond duration, you just need 25 microsecond. You don't need 125 microsecond. So but if you send all the signals one after another without any break, what you will have is one continuous mesh. So instead of that, and the signals will overlap on each other, cause interference. So there will be guard bands, guard durations. During those durations, no signal will be sent. So it is like this: one signal is sent, then there is some gap, then another signal is sent, then there is some gap, then another signal is sent. Now, to send three signals, you see there are three signal durations, one, and let guard duration be x. So let guard duration be x seconds, x microsecond. So you have, for three signals, you can see 1 x 1. So the total time is 1 plus x plus 1 plus x plus 1. So 3 plus 2x. Similarly, if you want to send 4 signals, you will see the time required will be 4 plus 3x. Thus we can say for n signals, total time will be n into 1 plus, there will be n minus 1 guard bands, so n minus 1 x. So for 25 signals, it is 25 plus 24x. Now 25 plus 24x has to be equal to 125 because that is the total duration that is available. So 24x is 100. So x will be 100 by 24, which is nearly equal to 4 microsecond. Slightly more than 4 microsecond. So 4 microsecond. So it is nearly 4 microsecond. So the correct answer is option A. 4 microsecond. So that concludes our class for today. Now for some extra time, Now we will look into mm, now we will look into another problem from the book BP Lathi. A signal band limited to 1 megahertz is sampled at a rate that is 50% higher than the so let us do so a signal is band limited to 1 megahertz and is sampled at a rate that is 50% higher than Nyquist rate and quantized into 256 using a new law quantizer. Okay, new law quantizer is not there. Okay, this one. The output of a SNR of a 10-bit PCM was found to be 30 dB. The desired SNR is 42 dB. It was decided to increase the SNR to the desired value. So there is a SNR that is 30 dB currently, and we want SNR dash as 42 dB. Now there is a 10-bit PCM, so L is so the SN signal power is same. So the main change comes from the change in the number of levels, because we know that SQNR, which is SNR in this context, because we are ignoring channel noise. So the SNR here is 3 so it is 3L square signal power divided by peak square. So signal power divided by peak square is constant. So we will not bother with that. Instead, yes. So SNR dash by SNR in linear. We have to convert this to linear, of course. So SNR dash linear divided by SNR linear is L dash square divided by L square. So 30 dB means SNR linear is 30 by 10 anti-log. So anti-log 30 by 10. So anti-log 3, which is 10 to the power 3, that is 1000. And SNR lin dash is See, 10 log SNR lin is SNR dB. So SNR lin is anti-log of SNR by 10. So SNR lin is 10 to the power 3 and SNR lin dash is 10 to the power 4.2. So L dash is L into square root of 10 to the power 4.2 divided by 10 to the power 3. So L into square root of 10 to the power 1.2, that is 10 to the power 0.6. Which is 3.98. So L dash is 3.98, which is 4. So 4L, 3.10 to the power 0.6 is 3.98, which means 4L. So fractional increase in transmission bandwidth. So if we increase the L, if we increase this L 4 times, then the transmission bandwidth means basically data rate. Data rate is dependent on the number of bits you are sending. So it is 2 to the power L bits you have to send. So previously it was 2 to the power L, and now the rate dash, this is R dash is 2 to the power L dash. So it is 2 to the power 4L. So the fractional increase in system bandwidth required fractional increase, this is problem 6.2-10 by the way, BP Lathi. Problem 6.2-10. So the fractional increase in transmission bandwidth, that is data rate, is given as R dash minus R by R. So it is 2 to the power 4L minus 2 to the power L by 2 to the power L. So that is 2 to the power 40. No, sorry, it's not 2 to the power 4L. It is, this is wrong. This is not 2 to the power L. It is 2 to the power, no, log base 2L, and this is log base 2L dash. It is not 2 to the power L. If you have L levels, you need log base 2L bits. So log base to 2L, sorry, rather log base to 4L. So this is log base to 4 plus log base to L, which is log base to 4 is 2. So 2 plus log L. So from the system bandwidth needs to change from 2 plus log L, from log L to 2 plus log L. So the fractional increase in transmission bandwidth is 2 plus log L minus 2 minus log L by log L. So it is 2 divided by log L. That is the fractional increase, 2 by log L. Now L, it was a 10-bit PCM, so L will have 2 to the power 10 levels. So log L will be 10. So this will be 2 by 10 or 1 over 5. So there is a 20% increase, 1 over 5 or 20%. So the correct answer is 20%. There will be a 20% increase in the transmission bandwidth. With this we end our class. With this we also end the problem solving session for analog communication of 2025. So that will be all from my side. This is Swastik Chakraborty. Thank you. Bye.